small mistake I made. I was not careful enough here. When I defined in that very, in the most general case, Borel action and the space of orbits, I was careless, and the quotient sigma algebra on the space x mod g should have been taken to be the universal one. I described it in two terms, which are not necessarily equivalent. One should take the quotient sigma algebra to be the largest sigma algebra such that the map x to x mod g is measurable. In many cases, for example, if g is, if x is a standard Borel space, and if g is locally compact second countable, it is the same as what I said. In a slightly more naive way, you push measurable sets, and you take a sigma algebra generated by all the images, but maybe the pre-image of something you pushed is not measurable a priori. So one should take care of this. I mean, I think in the way I described it, I was using this here, but you should observe that there is no need to use that description, that wrong description I gave when you observe this claim over there. I mean, this is true in any case. Just be careful when you do the exercise. Okay, so let me get back to the business. Good here. So I discussed. Soon I will move to another subject, which is Lebesgue spaces. What?
No, that is chaotic way of signing you.
So it's not more criticism? So let me make some more observation. So soon I will be moving to discuss Lebesgue spaces. Not only Borel spaces, but before I want to make some last observations about tame Borel actions. So proper actions, proper topological actions are tame. Clearly, I mean, you have a nice orbit structure. Orbits are closed, not only locally closed. In particular, any topological action, any continuous action of a compact group is tame. I guess I already see that, again, I'm still slopey here when I say any or proper without the second countability adjective and without the T0 assumption, and this is not true, but take a nice T0 second countable space. If you have a proper action, then it is tame. If you have an action of a compact group, this is tame. Because this is proper. Orbits are closed. Another theorem, which will be under our examination next week, but so I don't even properly define the terms now, but you should have this in mind. Every algebraic action of an algebraic group is tame. Actually, it is constructible. Maybe I will make one remark about it. This is a classical theorem of Chevalet. If you walk over an algebraically closed field, and maybe you know it, actually every map, every morphism of algebraic variety is constructible. This is the theorem of Chevalet. And I will only use it for oversee, or maybe I will switch to another algebraically closed field. But this theorem is also correct over any number. So this is more complicated. This follows from Borel's theorem about finiteness of Galois cohomology. If you are familiar with, I will not discuss these things. But you should know it. You should be aware of that. Okay, questions before I move to another subject?
The same, but not continuous.
Sorry?
But not continuous. Not continuous, right?
Oh, it is not continuous according to the definition I gave, yes. Okay, we will discuss Zariski topologies later on, we will see, yeah. So, yeah. when I define what constructible action is, I did assume continuity of the action, and those actions are continuous, but not with respect to product topology on G times X, but with respect to the Zariski topology on G times X, which is not a product. Yeah, so maybe, again, I wasn't just a little bit slow in the description. So now I want to discuss the Lebesgue category. For short, L space is accountably a generated space and those so accountably, this is Borel. With a measure class. So it is endowed with a measure, but actually I don't care about the measure. I care about all measures which are absolutely continuous to this one thing.
L space means Lebesgue space.
Lebesgue, yes. I will use the short-term notation that I will do. Yeah, let me keep it. Is that good? Unambiguous enough? Does it mean something funny in Polish? I don't know. Dot with the measure class of probability or sigma finite measure. So don't just put the measure that I don't know. A too ugly measure. Just take a nice measure. Every sigma finite measure is equivalent to probability measure. I just made this sum up to be able to put in the future sigma finite measures. For example, the Lebesgue measure on R is good. Okay, let me write down. Example. The Lebesgue measure on R. What is the standard notation for the Lebesgue measure? M, lambda, mu? It's also an eigenvalue. Too poor. Okay, so this I want to make this into a category. So the morphisms I want to consider are measure class reserving Borel maps defined up to null sets. So actually defined and identified up to null sets. Maybe I will write it down, it's important. So illustrate this. Whenever I have x here and y there, I'm writing down the isomorphism here if actually I can find a full set. And full is something I can define by means of a measure class. A measure class gives me nullity. It gives me the sigma ideal of null sets. And full is something that its complement is null. This is well defined. And I want to define an actual Borel map into Y or into a conal subset of Y. So this should be a Borel map, and it should be measure class preserving. That is, if you have a null set here, the pre-image of it will be null here. And by such a thing, I will think of a map, an actual map. I will call it a map from X to Y. And if there is another guy, X1, and another map, X to Y, I will consider these two the same. If, say, on the intersection, X intersection X1, they do agree.
Do you mean homomorphism of measured algebras?
So this is, yes, this is the same as homomorphism of measured algebras. I will make this remark. So equivalent description. If you are a logician, a morphism is a homomorphism of measure algebra. So the category of Lebesgue spaces is dual to the category of measure algebras with homomorphism only. It's not every measure algebra. The measure algebra should be standard. And this is, I took here countable generated. Or if you are an analyst, another dual category, equivalent category, is a category of commutative fundamental algebra. The category, this is the way I would like to think of it most of the time, but probably not in this lecture. The category of commutative, so the full subcategory of fundamental algebra, which consists of commutative ones. Commutative von Neumann. Algebra. Whenever you have a Lebesgue space, X, I can consider L infinity X. Whenever I have a map from X to Y, I can pull back an infinity function from Y to X and get a map from L infinity Y to L infinity X. And this would be a map of these objects, and let me emphasize, when is a commutative fundamental algebra then equivalent or isomorphic to the L infinity function of a Lebesgue space of something which is, I don't know, 0, 1 with a Lebesgue measure, say, or a countable measure on a countable set, or union of such things. This is if and only if, which are weak star separable. On L infinity, to L infinity, I have a redo, L1. A fundamental algebra is actually, W star algebra is the synonymous. Is a C star algebra which has a predual. Okay? The predual of a commutative algebra, which on the algebra you should think of L infinity of something, the predual is L1. Same thing. And I want this L1 to be separable. I want L infinity to be separable with the weak star topology, and this is the same as this standardless assumption. So the standardless assumption, which may appear, I don't know, well, it's some probability assumption, of course, but it is very natural in this set. So from this point of view, it's very useful. Maybe I will come back to it as a remark in the future. But usually I will denote the space of morphisms x to y. I will denote mainly, I guess, maps x, y. I will put, not now, but I will put maybe a subscript g here if I want them to be commuting with some g action. I need to define a g action here. But when you do ergodic theory, or when you do analysis, many times we want to consider, like in the L-infinity function case, maps from this category to the former one. Maps from Lebesgue spaces into Borel spaces. So let me explain what I mean by this. It's very clear. For a Lebesgue space X, Borel space, typically standard, U, I will use the symbol LXU to denote is a space, as you would guess, of Borel maps defined and identified up to null sets. So it's classes of functions, not actual functions. But you're familiar with many examples of that form, L-infinity, L1. Of course, many times one puts subscript here to say, I know I want some integrability of whatever kind. I want some equivariancy of whatever kind. Okay, so this is the carry of some further symbols. But just keep in mind that this space maps xy and LXU are of a different kind. And in fact, LXU has a natural structure of a Lebesgue space by itself. Sorry, for Borel space by itself. I'm not sure about what is the structure of maps xy right now. Okay. So let me remind you something we discussed yesterday. So the category, not the category, the isomorphism classes in the category of Lebesgue spaces are quite dark. I mean, you don't have a big variety of them. Every Lebesgue space is Lebesgue isomorphic to either, well, a finite one. In the terminology of phenomenon algebra, this is called 1 sub n, such a thing, if you ever see. This 1 sub infinity. Well, you may have 0, 1. And union of such. Of course, when I consider those spaces, these are coming with the natural meta classes. The big one here, counting here. Do I forget anything? So you may think that this category is not interesting because you don't have many isomorphism class, but of course categories are not just spaces. These are the arrows too. And the arrows are what is interesting. If we take group G, for example, I might want to embed it in the group of isomorphism of this Lebesgue space. And this is what ergodic theory is about. Actions of group on Lebesgue spaces. This is the theory of Lebesgue action. So you want G, in order to define such a thing, you want G to be a Lebesgue space itself. So you want G, the group, to have some Borel structure and a measure on it. So the natural candidates should be locally compact groups, which have the Haar measure on them. You want things to be countably generated. So I will take always, considering ergodic theoretical questions, my group will be second countable. So G, locally compact, second countable group. Many times probably I will use the short term LCSC group. G goes to the Borel, the Lebesgue isomorphism of X, and I want this structural map of the action to be Lebesgue. Example. First example I should give is the action of G, such group, of course, on G mod H. So we discussed this example. We discussed actually in the past the fact in this class. So how measure on G, and so this was in the tutorial class. G mod H, a coset space, when H is a closed subgroup of G, always have a canonical Haar measure class. Not necessarily an invariant measure, but there is always a G invariant measure class on it. So this is an example of a Lebesgue space, or a Lebesgue action, this thing. So maybe there are some details to fill up, but this is quite easy, and this is very, very classical, of course. I should say that, and we did discuss this in full, that sometimes you do have invariant measures, sometimes you don't, and this is important distinction. So if you have, I introduced some notation here before. I don't discuss this in full, but of course, if you do act on a finite set, you always preserve the counting measure. Also, if you act on a countable set, if you act on 0 and 1, sometimes you do preserve a probability measure, sometimes only the measure class. Sometimes, if you think of the action of R on itself, you do preserve a measure, but only a sigma finite measure, not any finite measure. So standard notation for this will be 2 for finite measure preserved, to infinity for infinite measure preserved, and 3 if you have an action which does not preserve any measure. Again, I'm not defining this properly, I'm just putting those symbols on the board. If you ever see them, you should think of the relation with ergodic theory. Those symbols appear naturally in the theory of Von-Neumann algebra and the classification of factors. Okay, now I want to discuss something very beautiful. I want to say, well, previously we had this in the last lecture, actually, this is the context of this term, and we discussed the fact that every Lebesgue space could be made compact. It could be, I mean, essentially, it could be identified with 0. Now, Now what about actions? What about the category of the backspace? Can I take this category and represent it into the category of topological spaces? Can I find the representations of all spaces as topological spaces and all maps are topological maps? Of course not. I mean, just take all automorphisms of 0, 1, and you cannot represent these as some homeomorphism group of a topological space in a nice way. By the way, when I say nice way, I mean I want metrizable spaces. You don't come for me with hyperstonian spaces, please. Not here. What I want to emphasize now is that I can do it, but for countably many morphisms at the time. Okay, so let me start with forming observation. So this is observation once we understood how to find a Cantor model to a Lebesgue space for a Lebesgue map. X to y, or a Lebesgue map X to y, we can present, and I hope my terminology is clear, I am not fully making all the definition, we can present as a continuous map of compact metrizable spaces. So I can find a compact metrizable model for X and a compact metrizable model for Y with some measure. So I can find, to be precise, a compact metrizable space with a measure on it, which will be Lebesgue's compact. Same thing for Y, such that the map here will be represented by a continuous map. And this is very easy. If you remember how we did it, we will just use Cantor sets here. It's very easy if you remember how we did it for one space. So for Y, so here's the proof. For Y, choose this countably generating collection, countably generating collection. Maybe I call it Bn, reserving An for X, Bn, and defined Y to the Cantor set as we did before. Y goes to Bn, Y, okay? And I'll do the same for X, only when doing in each for X, I will make sure that the natural map between the two spaces will be continuous by making care that the pre-images of open sets, or the sub-bases of open sets here, will be open. For X, choose such a collection and enrich it. Make sure of including all the phi minus 1 Bn. And let me term it as An, AK, take another index. To make it too confusing. Is it clear what I'm saying? And let me mark again X to 0, 1 to the end in a similar fashion. And you have Y, and we mapped Y here. So how the set of indices is not the same. This set is richer. And I'm having, maybe I should think of it as N, union N here. I'm describing a proof. I'm not giving all the. I'm explaining. One n is the indices of the generating set of for x, and one for the pre-images pushed from y. And this projection is actually coming from the push, and the pre-image of an open set here will be open here. So the thing is that what is this contouring of a space? If you have 0, 1, the interval 0, 1, well, you have some functions are continuous on it, but if you want the characteristic function of 0, 1 half to be continuous, well, it is not on 0, 1, but I can cut it into two pieces, and on that model of the same space, measurably or legally, these two things are just the same. If I didn't happen to have an atom at 1 and 1 half, these two things, the interval 0, 1 or the third apart interval, are the same space, but the characteristic function here is continuous. And then this is what I'm doing here, countably many times. So again, I leave it for you to fill up the details if this is not clear. Maybe I will give another approach, slightly more sophisticated to the solving the same problem, slightly more sophisticated, but somehow something that helps sometimes. A compact model for x could be given as well by picking a compact model 2x is the same as, think of it, a choice. Oh, and when I say compact model, I always mean metrizable. In this sense. Of a weak star dense, non-closed sub-algebra of L infinity x. So when you choose a compact model, basically you choose which functions you want to be continuous. You have all functions on x, and you want some function to be continuous and some not. Oh, well, you want all of them to be continuous, but when you take all of them to be continuous, it's like taking the Gelfand spectrum of L infinity x, which is a wild space. It is not metrizable. So I want it to be metrizable, so this is why I want it to be, did I write separable? Separable. This is an important wording, which I forgot. I want a separable sub-C star algebra. So it's separable from the norm point of view. So this will make it a C star algebra, and it will have a spectrum which is a compact metrizable space. Metrizable reciprocity again. But it will be rich enough to fill all the measure because it will be W star dense. W star is the functional of integration with respect to L1 functions. L1 function, if you think of it, not in terms of functions, but in terms of density, L1 functions are just absolutely continuous functions with respect to that given measure that we have. We specify on our space, the Lebesgue space X, we specified a measure class. L1 is just, again, don't think about it as functions now. These are all representatives of that class. When you think about, by the Radon-Nikodym theorem, all representative of that class or weaker classes. So this is the L1, and we want our space to be endowed with a measure saying this. So this is a choice of a compact model, and just if we have the map, let me be brief about it. If we have a map x and y, I can choose such a guy in L infinity y, and choose such a guy with L infinity x, containing the pre-image of this guy. Sorry, other way around. I have L infinity x goes to L infinity y. What is the one? Oh, okay. Figure it out. I want to rush in order to. I thought I would do much more. And now, so this I did only to one function, but now here's the important theorem. Every Lebesgue action has a compact metrizable model. So again, let me give a sketch of proof. First, where G is countable. Maybe it's much easier to understand. Just do that. Take X, take a collection of sets separating the points, but enrich this collection of points to be gamma invariant. Whenever you take Bn, take little gamma of Bn running over all gammas. This is still countable by the countability of gamma. And this collection, when you give, when we construct this Cantor model, will be, because gamma will act on the space of indices, will be acted upon by gamma. And because gamma will just act on the space of indices, it will respect the topology. And this will be a continuous action. Is this construction clear? Again, I don't want to write details on the board now. So I just write Cantor model. Model rich enough. What about GLCSE in general? The best solution to the problem that I know is to use this kind of point of view. So for GLCSE, there is a name to this question, basically, and there's a name to the theorem. This is called Mackey point realization theorem. Or, well, Mackey point realization is something very close to this. It's not exactly that theorem. But actually, from the point of view of four-normal algebras, this is very easy to do. I will only give a very, very brief sketch here. And it is the following. We just want to take in L infinity x such an algebra with all, subalgebra with all this adjective. Weak star dense, non-closed, separable. But G invariant. Okay, so somehow if you just start by taking something and multiply by all G's, it is not good enough, even though that G is second countable. Somehow, if you take just a separable group, this is not good enough. You can't do it. The theory is not correct. What you need to do is to use L1 of G. Just start with any algebra of your choice, satisfying everything like here, and say A, and take all convolution image with L1G functions. And then this will be the algebra that you close it up. This will be the algebra, which is G invariant and rich enough, but still separable, that you need. Okay? So this is really, really very brief. And now a corollary that we get for a Lebesgue action. Almost every stabilizer is closed. Whenever you have a Lebesgue action, you can think of it as a continuous action. So stabilizers in G are closed. Almost every stabilizer are closed. And the orbits are measurable. Okay. this. You don't need that theorem for that. Orbits are measurable because, well, our group G is sigma compact. There are union of compact sets in the compact model. Countable union of compact sets or countable union of closed sets, so measurable. What else? Okay. Now I want to state, I thought I would prove, but I'm not sure I will have the time, the very important theorem of this integration of measures. So I will first state it as a theorem about continuous function between compact metrizable spaces, but by those kind of tricks, this theorem that I'm about to state, this integration of measures, will be valid for Lebesgue spaces as well. Maybe I'll give a little sketch of what I'm about to do. So this is kind of a Fubini theorem, but for vibration, not for products. So assume you have some sort of a product space, or a space fibered over another. And assume you have a measure here, nu, and on each point y, you have a measure on the fiber, mu y. So you have this family of measures, and it varies nicely, I mean, measurably in some sense, with respect to the structure on y. Then I can integrate function using this collection. If you have function f, I don't know, 0, 1, I can restrict it to the fiber, essentially, ignore almost everywhere issues, etc. I can just take f of x d mu y x. Just use that measure, but I can do it for every single y. And for every single y, I will get a value here. This result, this is a number, it will give me a function to 0, 1. And I can integrate, this maybe we call it f bar, and I can integrate this f bar with respect to d nu. So this is integration over x, this is integration actually over xy, and this is integration over y. And this is a way of integrating functions on the full space x, on total space. So this is a measure. It gives me a measure. A way of integration is a measure. And this measure is denoted the integral of the mu y with respect to d nu. So this process I described here very briefly is the process of integrations of measures. The theorem that I'm about to write down and wanted very much to prove, but probably will not, is the converse. Every measure here comes about this way. And again, I will state it now for compact spaces and continuous map, but this is not really an issue by those theorems that we described. A continuous map of compact metrizable spaces. Let mu be a probability measure on x. So this is, you should think about it as the result of this integration. Now here's something which is very easy to do. Define nu on y as in push. Just before I I continue. Is it clear? How do I push measure? Let me nevertheless say, mu is a functional over here. I want to define a function over here. If you have a continuous function here, just compose C to the function here, mu integrated. This gives me a function on the space of continuous functions here. Or if you wish, if you have a set here, pull back, this is a set here, mu measure it. This gives me a measure of that set. It satisfies all the nice properties of measures, and this gives me a measure on Y. This is a push. So this is why what is less trivial, this is very, very easy operation. What is less trivial is disintegrating mu with respect to this nu. Then there exists a map. Actually, this is a map it goes from Y to the probability measure on X. Y goes to mu Y. It is nu almost everywhere defined. Even if everything is continuous to begin with, everything is as nice as you want, the disintegration process actually is a process that lives in the Borel or the Lebesgue, in fact, world. It will not be continuous, this map. It will not be everywhere defined. Such that, and this is a space of probability measures of X. Mu Y actually is supported on X sub Y is a fiber over little y. And then what I'm writing here is, of course, for almost every little y. And most importantly, mu is the integral of the mu y d nu y. And this makes sense in that form.
Sorry, but the map is on fibers. This measure is in fibers.
Well, yeah, I mean,